guys, welcome to another live stream. So if you're watching this as a live stream, I guess you can get ready for this sort of long live stream that I'm going to be doing related to the rates of a reaction. We're going to have a look at factors, we're going to have a look at literally everything: physical, chemical changes. We're going to have a look at speed of a reaction, we're going to have a look at reversible reactions, redox reactions. So everything related to rates of a reaction in the chemistry IGCSE syllabus. So if you do this syllabus, so for chemistry, then I believe this should be okay for you. Anyway, I think we will start to begin, and also, yeah, let's just begin with the video. So we're going to start with the notes, and then we're going to move on to the actual post paper questions, I believe. Now you can find all of these notes in the description. So I'm using the site Save My Exams for this because I believe they have the best notes for this topic. And also I'm using Z Notes, which I believe you must have heard of. They do notes for many IGCSE syllabus topics. Okay, so I've put two links for the two notes, and then I have the past paper questions that we will be having a look at the end of the live stream, so that we can actually use our knowledge that we've learned in the first half of the live stream in relation to the questions that IGCSE asks you. So let's see how much we can do in this live stream. The main focus is to finish the rates of a reaction, which is topic 7. Okay, so rates of a reaction, let's just begin. First of all, let's start with physical and chemical changes, actually. So we're going to start with that place. And that's the first chapter in this sort of syllabus on this topic. Okay, so the first thing you need to know about this, okay, physical changes, chemical changes. That's the first thing you need to know. Okay, so if you're watching this live again, you can get your book, write some notes while I'm talking, and if you're not, also, you can do the same. But yeah, okay, so let's begin. So first of all, physical change, from its name, physical. Okay, physical and chemical. So chemistry, okay, from its name, you can find an aspect of chemical in the name. Okay, now chemistry deals with all substances, mixtures, reactions. We have a look at all of that, right? So what is the difference between a physical change and a chemical change? Okay, that's what we're going to be learning in today's live stream. Not only this is going to be the basic of everything, and I'm sure you must have actually learned about physical changes and chemical changes. It's quite an easy topic. So first of all, physical changes. What's a physical change? A physical change, such as melting or evaporating. Melting is simply like, for example, an ice cube. When you put it in a glass, you see after a few hours it will not be visible. It's going to be melted into a liquid form. Okay, so that's an example, ice melting. So that is a physical change. Then we also have evaporating. So evaporating is when you're cooking, and that gas that goes up, or that's called vapor, or water that's going up, that's called vapor, and that's called evaporation. Now, if you've watched my video on, I believe, the states of matter, you should be knowing all these sort of states of matter. And we are simply linking everything together. Now, physical changes are simply, these are things that don't produce any new chemical substances. So what this simply means that if I react to things, for example, I will not get anything new, which is chemical, okay, which is a chemical. It's not a chemical substance, but instead it will form something that I can reverse, okay, or in simple ways, I can easily reverse, okay, these mixtures. So that's what we say, and these are relatively easy to reverse, and mixtures produced are usually relatively easy to separate. Okay, we move on to chemical change. Okay, so chemical change, from its name, okay, chemical reactions, okay, in a chemical reaction, why are they called chemical reactions? This is because new chemical products are formed, okay, there's a chemical change in a chemical reaction, okay. So we have physical reactions, or I don't think we call them physical reactions, but simply in chemistry terms, we call them a chemical reaction. Now, first of all, you need to understand, or you need to know, that new chemical products are formed when a chemical reaction takes place. Okay, now you might ask me, what are these chemical products that are formed? Okay, now let's give you some examples. Okay, now a simple reaction, okay, of maybe salt and an acid. Okay, sorry, maybe a metal and an acid. Okay, sorry, it'll form a salt. Okay, but in a metal, for example, sodium. Okay, sodium reacts with hydrochloric acid. Okay, hydrochloric acid is a chloride, so that will form sodium chloride. Okay, sodium chloride is a different chemical product in that reaction. So that means that that reaction we say is a chemical change. Now I cannot convert that sodium chloride back to sodium and then hydrochloric acid. And that's why we say they are chemical changes. So that's a quick way to differentiate between a physical change, okay, and a chemical change. A physical change, um, is a very good example that is known is ice melting. Okay, after ice melts, I can freeze it and then I can melt it again and repeat the process several times. I can get the same state of matter several times, and nothing is forming new. It's just the same product in a different state. Okay, that is what we say are called physical changes. We say we move on. Most chemical reactions are impossible to reverse. Okay, that's a key word there. Impossible to reverse. Okay, so in a chemical change, in simple terms, it is impossible to reverse. Okay, it is impossible to reverse. You cannot reverse anything in a chemical change. Okay, then we move on. I think these are some examples. So energy gives changes also accompany chemical changes. Okay, later on, I think we'll get to know about, how can we tell this is a chemical change? Okay, how can we, sort of tell? Now, I think it's not in these notes, but simply we have different ways we can determine something is taking place. Number one is the smell. When something is reacting, that smell, okay, that's produced. That smell produced can give us a sign that a chemical change has taken place. Let's give you another one. For example, when you are heating something and it starts to bubble, whenever it starts to bubble, we know that some chemical change has taken place. So those are just some examples of how we can tell it's a chemical change. Okay, so that's some of the examples we can know if it's a chemical change. So in an exam, you can get a question, okay, and it says, this has reacted with this. Is it a physical change? Is it a chemical change? Now, with the knowledge that you have between these physical changes and chemical changes, you can determine this. Now, you can also get this in the multiple choice test, which is paper 2, so you can also get it in that. Okay, so we have different ways these questions can be asked. So these are moreover direct. It can tell you, is it a physical change or is it a chemical change? Or sometimes they can ask you, this reaction is a chemical change. Okay, this reaction is a chemical change. Now state two ways we can tell a chemical change has occurred. Okay, and you simply write a smell, or then you can also write bubbling. Okay, and you will get your marks at that position. So you can see physical change and chemical change are more direct. So there's not that much to add on to this except knowing what physical changes and chemical change is. Now, later on in the end of the live stream, we will do some questions on the physical change and chemical change. Now, let's move on and let's have a look at the speed of a reaction. Okay, the speed of a reaction. And this, now we're going to have a look at the factors that affect this reaction. Okay, what are the factors when I react with two substances? What happens there? So let's begin. Number one, it says the effect on concentration. Okay, an effect on concentration of a solution. Okay, so the first one that we are going to be talking about is the effect on concentration. So number one, you can see this right here. If you've done biology, you can tell this is a low concentration. Okay, this right here is simply a low concentration box. Okay, while the one right here is a high concentration. Okay, low concentration, we can tell the molecules are quite less, or we can say the concentrations are quite less compared to the volume that it has. But when we have the high concentration, you can see there are many sorts of molecules present in the particular volume. Now, how does the effective concentration affect our reaction? Okay, that's the main thing we're going to have a look at. So let's have a look at the explanation. It says that an increase in concentration of a solution Okay, an increase in concentration will lead to an increase in the rate of the reaction. An increase in concentration will equal to an increase in the rate of a reaction. Okay, so it's quite straightforward there. Okay, when I increase the concentration of a reaction, this will give me the ability to have a quicker rate of a reaction. Now, you might ask me, why do you want a faster rate of a reaction? Now, let me tell you something. Okay, some reactions that we know in chemistry, they take months, they take days, okay, they take years, okay, some of the reactions. And therefore, scientists came up with ways we can speed this reaction so we can get the results quicker. You think I will wait for 2 years and then, find out my results? No. In chemistry, we use external effects or external causes so we can get our results much faster, and effective concentration is one of them. If I increase the concentration of my reaction, I'll have a faster rate of reaction. Okay, it will increase. Now, what is the reason for this sort of type of thing? Why, if I increase the concentration, why will my rate of reaction increases? Now, first of all, I told you we have particles. Okay, if I increase the concentration, we'll have more particles. Okay, and if I have more particles, I will have a more frequent and successful collision per second. Okay, in this case, you have not yet learned it, but we say this is called the collision theory. Okay, this is called the collision theory. Now, this is just one set of my notes, and then later on, I will tell you what collision theory is, what is kinetic theory, and I'm sure you've heard of kinetic theory, but I'm not sure if you've heard of the collision theory. But in the concentration sort of scenario, is why the collision theory is the one that is in charge of the rate of the reaction. Okay, hopefully you understand that, because when I increase the concentration, I will have more particles. As you can see in this diagram, if I increase the concentrations, I will have I have more particles. If I have more particles, that means that I'll have more collisions frequently. And if I have more collisions, then that will allow me to have an increase of the rate of reactions. Okay, because everything in related to reactions is dependent on the collisions between the particles. If I collide much quicker, then my reaction will be much quicker. Okay, so this concentration uses the collision theory, and let's move on now. The next one is the effect on the surface area. Okay, now in IGCSE you need to know three. Okay, you need to know temperature, you need to know surface area, and you need to know concentration. Okay, they will at least ask you one of those. Okay, now you have catalyst and you have light and you have all of that, but those ones are rarely brought up. The three ones that you need to know is concentration, surface area, and temperature. So let's move on to surface area. Okay, so we have a bigger surface area right here. Okay, bigger surface area to a smaller surface area. Okay, so this is the volume ratio 1 centimeters to a volume ratio of 3 centimeters. It's getting bigger right here. The surface area is bigger in the last image compared to the smaller one. Okay, and in this you can see that the diagram shows the surface area, okay, of the various cubes. Okay, and now let's get the big question out. Why does surface area matter in a rate of a reaction? Now the explanation would be quite easy. Okay, now an increase in the surface area, okay, of a solid will increase the rate of a reaction. Now this is because the more the surface area these particles have, the more they have space around the other reactant, there will be more frequent and successful collisions per second. Okay, because they have room to collide, there will be more successful and frequent collisions per second. And this one again applies to collision theory, and this collision theory basically simply states that the more collisions you have, the faster the rate of reaction. Okay, sorry about that. I'm really sorry about that. Anyway, let's just move on. And I was talking about surface area. Okay, and surface area is simply saying that an increase in the surface area of a solid will simply lead to a faster rate of reaction. Okay, and hopefully you do understand that. Okay, so let's move on. And now let's finally talk about the next thing. And again, the explanation to this is simply that this is because the particles have more space to roam around. Okay, and therefore there will be more collisions and more successful collisions, and therefore we have a faster rate of reaction. Okay, so that is the simple explanation to this. Okay, let's move on now to the effect of temperature. Okay, the effect of temperature. Okay, so let's finally move on to the effect of temperature. Okay, so an increase in temperature will lead to an increase in the rate of a reaction. It's as simple as that. When I increase my temperature, I will simply have a faster rate of reaction. Okay, so it's as easy as that. Okay, and yeah, let's move on. Okay, so if I increase the temperature, I'll have a faster rate of reaction, and this theory is used by the kinetic energy theory. Okay, it doesn't use anything else, but instead it uses the kinetic theory um, sort of thing. And the kinetic theory says that it's basically the energy provided in this chemical reaction, and the energy that is given in this will help it to go much quicker. Okay, so that's how everything works. Okay, now we finally move on, and we now say that because of this kinetic theory, we also have something what we call the um, we also say that we have the collision theory in this effect of temperature. Okay, now with the collision theory, we say that because there will be more energy, there will be more collisions, and therefore increasing the rate of the reaction. So when we're looking at the effect of temperature, we're looking at both the kinetic theory and the collision theory. Okay, so let's move on. The next one is the effect of using a catalyst. Okay, using a catalyst, and you can see this diagram right here. Okay, this diagram which simply states, okay, so we have the reactants which is on green right in this chart, and then we have the activation energy. Okay, this is the activation energy, and then on top right here, all the way from the starting point, that is the energy that's gained, and the lower energy we also have seen that is using a catalyst, and then therefore the overall change in energy is right here. Okay, so this is a quick diagram to show how much energy is used and then how much that results into the temperature. Sorry, not the temperature, the reaction. Okay, so that's quite straightforward and quite simple, I'd say. With the catalyst, it simply says that catalyst will reduce the activation energy. Okay, and instead of having to use the energy, it will use another path that requires lower activation energy, and therefore the lower the activation energy, it has a different route, and therefore it will allow more successful and frequent collisions. And this basically shows that when a catalyst is used, the rate of a reaction will increase. And I'm sure if you've gone to the chemistry lab, I'm sure you must have heard of the fact that we use catalysts to sort of find our reaction results in a quicker way. Okay, now explosive combustions. Okay, explosive combustions is what it's not a factor, but we have to look at it. Now, combustion is simply explosive combustion is when there are many fine particles in the air. Okay, when there's so many particles in the air. Okay, like for example, in the industrial processes like metalworking, coal mining, or for milling produces very fine and tiny particles. Okay, when this reaction happens or when this process happens, it produces these tiny particles. Okay, and these particles have a large surface area and are combustible in air. I hope you know what combustion is. Combustion is simply like fire, okay, or it's like explosive. Combustion is a burning, okay, in simple words. Now, even a small spark will make them ignite, and since the surface area is so large, the rate of reaction is so fast, they will be explosive. Okay, and methane gas is mixed with the air in coal mines, so it can form an explosive mixture. Okay, so that's more of like a sort of property that you need to know. Okay, so in this say they're simply comparing the way these chemicals are so dangerous. Okay, the rate of a reaction happens so fast that it's even hard to keep track of them. Okay, then we move on. Let's move on. And now let's have a look at the concentration. So now we're having a look at interpreting data. Okay, so here we have sort of a concentration graph. I'm going to just zoom out a bit. Okay, like that. So hopefully you can see now more clearly. And it simply says that the amount of products is the same in both reactions, and only the reaction is different. Okay. Okay, so that is that. So what this basically means that when the reactant, okay, when the amount of the product is the same um, as in both reactions, only reaction rate is different. So if you even put the same sort of products, the same sort of thing, the only thing that will be here is the fact of the reaction rate. Okay, when there's a higher concentration, as you guys can see, it's more steeper. Okay, but when there's a low concentration, you can see it's more lighter, more lower. So this is simply a diagram right here to show us the way these factors affect them so much. Okay, so that's quite direct and quite sort of okay. So hopefully you guys understand from that. Just a quick diagram to show you how the different types of factors affecting a rate of reaction can be measured. Okay. And we move on, and next one says that the explanation is because when compared to a reaction with a reactant at low concentration, the graph line for the same reaction but at a higher reaction has a steeper gradient. So what we've observed from this sort of graph is that if we have high concentration, remember, increases the rate of a reaction. So if we have a higher sort of concentration, then it will result to a faster rate of reaction, and therefore we'll have a steeper gradient in the graph. Okay, so we move on then, and it says that this shows that an increasing concentration of a solution will therefore increase the rate of a reaction. Okay, let's move on to particle size. Okay, now here we have another graph. Okay, and this graph now talks about the sort of particle size. Okay, and this one says that the greatest surface area, so we have the pink line that says the greatest surface area, and we have the green line which says the smaller surface area. Okay, so the explanation is here that it's quite similar to the other one. It says that when there's a greater surface area, there is a faster rate of a reaction and therefore a steeper gradient. But when there's a smaller surface area, there is a less gradient. So gradient is basically the steepness, if you didn't know, and you must have heard of this in math, gradient, to calculate gradient. So it's similar to this. Okay, so gradient is simply the slope, the steepness of a line. So you can see that the gradient is higher when there's a surface area. Okay, and the same now here is for the catalyst. There's another diagram right here for the catalyst, and this one is similar. We have already looked at it, and it says that when there's a catalyst used, it uses an alternate path and therefore increases the rate of a reaction with a lower energy, and therefore more collisions. Using the collision theory, it will increase. Okay, now let's have a look at some examples, okay? Because in chemistry, or in most of these sort of exams, what they do is that they give you a scenario, okay? They give you an example, okay? And you have to figure out how to do the following, okay? So let's do it. Now, extended only, okay? So this means that if you're doing the core paper, you will not be wanting to, you won't be needing this. But I think most of you guys will be doing extended, so therefore I'm going to have a look at extended. So the first thing is saying the effect on the surface area of a solid on the rate of reaction. So the first reaction that we're going to have a look at is the surface area. Okay, and we've known that the higher or the bigger the surface area will result to a faster rate of a reaction because the particles will collide more often and more successfully, and therefore will lead to a faster rate of a reaction. Okay, so now how can we test this? Okay, so we're going to use an experiment to do this. So you can do this in your chemistry lab. You can ask your teacher to do one of these experiments too. So the first thing you need to have is a conical flask. So this diagram that you see right here is called conical flask. Okay, now this conical flask right here will be containing, we say, dilute hydrochloric acid. Okay, dilute hydrochloric acid. And then we are connecting it to a trough. Okay, which you're connecting it to a trough, and this is just a glass rod. If you are wondering, it's not any condenser, it's nothing like that. Okay, so you're just connecting it to a trough. Okay, and in this trough we have a beehive shelf, and then we have water till the top. Okay, and we'll see why we need water, because in the later on we'll get to know that to this reaction will collect gas faster. Okay, and the water will be displaced then. Okay, so you have the measuring cylinder right here with water, and then you have the conical flask, and you've put a stopper here, and that is that. Okay, next up, you add calcium carbonate chips to the acid. Now whenever you do add calcium carbonate, so this is a good experiment you want to know. Okay, whenever calcium carbonate, okay, is added to the hydrochloric acid, okay, what is this gas right here? Okay, what is this gas that is formed right here? Now this gas right here is carbon dioxide. Okay, and we've learned that. Okay, whenever something reacts with the carbonate, we have water that is formed and carbon dioxide. Okay, so in this sort of reaction, when this reaction happens right here, when the calcium carbonate reacts with this hydrochloric acid, it will release the gas, will come down right here and will displace the water, and this gas right here is carbon dioxide. Okay, now you can repeat this test. Okay, but maybe this time you don't use chips, but you use powder. Now remember, the key word right here is calcium carbonate chips, and then calcium carbonate powder. Calcium carbonate chips have a larger surface area and therefore will have a faster rate of a reaction, but the powder has a smaller surface area and therefore will lead to a bit of a slower reaction. Okay, and you can see right here is the method that you can also do it at home. Sorry, not at home and the chemistry labs, but you simply add dilute hydrochloric acid, use a capillary tube or it's simply a glass tube, and connect this to a flask, to a measuring cylinder upside down, and then to a trough, and then you add calcium carbonate chips. Okay, and then there'll be a reaction and we'll have some gas formed. Okay, and then you can also time this. You can time the rate of reaction. You can time how long it took, for each of the following to react. Okay, so it's quite simple and good and easy. So the results would be the smaller size of the chips causes an increase in the surface area of the solid. Smaller sizes of chips causes an increase in the surface area of the solid, so the rate of the reaction will increase. This is because the surface area of the particles will be exposed to the other reactants, so there will be more frequent and successful collisions, and therefore increasing the rate of the reaction. Okay, so hopefully you do understand that. So that's how surface area is affected. We move on to concentration of a solution on the rate of a reaction. So number one, add acid to the sodium thiosulfate to the solution and start a timer. So this time we're having concentration into the sort of picture. So in this case, okay, we are using different concentrations, as you guys can see. We're going to go through there, but we're going to have using different concentrations, and that's how we look at the rate of a reaction. Now, it's not quite that important to know all of this, but these are just some examples on how we can sort of do these experiments, okay? So let's move on directly to temperature and concentration. Okay, so here we'll have a look at concentration, and then we'll have a look at temperature. So first of all, temperature. Particles need to have a minimum amount of energy to react when they collide, and this we call is the activation energy. Okay, this we call the activation energy. Okay, and at low temperatures only a small number of particles will have enough activation energy, so the reaction will be slow. But at a higher temperature the particles will have more kinetic energy, and therefore they will move faster and with more energy, and the collisions are therefore more energetic, and there is a greater number of particles with a sufficient energy to react. Okay, so here is just some more examples, and the same thing to concentration, so it's quite similar to the rest. Okay, now we're going to move on. Okay, we're going to do a sort of paper that is dealing with physical and chemical changes. Okay, so before we move on, we are going to be answering this question right here. So this is again in the description, so you can find it out there, but I'm simply getting it from PMT, and the notes were from Save My Exams, so all credits goes to them. So now we're going to do sort of questions. Okay, now these questions are from the IGCSE syllabus. Okay, this means that they've got all these questions from the IGCSE papers. Okay, so they've just combined everything into one. Okay, and now let's finally have a look at this. Okay, so we're gonna have a look at this and we're gonna answer it. It's quite a bit of a long paper, but let's see what we can do with the following things. So let's see if we have revised enough. Okay, so let's move on. It says biological catalysts, okay, produce microbes to cause food to deteriorate and decay. Name name these biological catalysts. Okay, now if you do biology, you should know this answer. And simply one of the example of a catalyst is called enzymes. Okay, this is a biological catalyst, enzymes. Okay, now I'm not going to be writing throughout this live stream because again my handwriting is really bad. Now let's move on to the next one. It says that freezing does not kill microbes. Okay, freezing does not kill these microbes, suggests why freezing is still a very effective way of preserving food. Okay, now you've noticed that whenever we have leftover food, we put it in the fridge. Okay, why do we do this? Okay, now in relation to enzymes, okay, I'm gonna give this example in relation to enzymes. Okay, and you can say that when you put it in the fridge, okay, microbes will not grow. It will reduce the growth of these microbes, okay, because microbes reproduce, okay, and they become many and many. But when they're frozen, okay, when they're cold, they cannot, or they simply reduce in the growth. And because they're reduced in the growth, there will be fewer enzymes to decay the food, okay. Or you can also say that one of the very good answers you can write in here is that enzymes work well at high temperatures. Okay, and we've learned that in the rates of a reaction, and we've said that the higher the temperature, the faster the reaction. But with a lower temperature, enzymes will be less effective. This catalyst will be less effective. Okay, and therefore this will lead to a slower reaction rate, and you will get your 2 marks there. The next one says that pea seeds grow in pods on pea plants. Okay, and freshly picked pea seeds contain sugar. The sugar can be form a polymer. Okay, and give the structural formula of a polymer and the name of the product of this. So okay, so now this is not that related to physical and chemical changes, I would say. So I'm just gonna quite skip that. But a good product of this would be water. Okay, sugar and water. But we have not yet learned polymers in this live stream, so I'm gonna not do that question right now. And it says describe how a pea plant makes sugar such as glucose. Now this is more like a biology paper, if you've noticed. Okay, so if you do biology, you might be in luck, because if you do chemistry and biology, it's quite similar. Okay, and this basically is a process called photosynthesis. Okay, or we can say photochemical or light or something like that. Okay, and photosynthesis needs two reactants. It has carbon dioxide and water needed, and this will combine together and will form glucose and oxygen. Okay, so glucose is also a type of sugar. Okay, so we move on. Number two, it says that the table gives the melting points and the boiling points and the electrical properties of six substances A to F. Name two substances that could be metals. Okay, let's see. First of all, does not conduct electricity. Okay, so we already know that this can't be the answer. Okay, because metals do conduct. So boom, cancelled, boom, cancelled. So we have this, boom, cancelled, boom, cancelled. So the answer is C and F. Okay, and I got all this information just because of conductivity. Okay, so the answer is C and F. Okay, we move on. Which substance could be nitrogen? Okay, now nitrogen has a quite low melting point and has a very low boiling point. Okay, it has a very low boiling point. So that's what will give it off. Okay, and you can see from the all of these, you can see that A has the lowest boiling point, and therefore we know that it can be A. So remember, nitrogen has a very low boiling point, and therefore we can get the answer of negative 196. So A is the answer, and it says which substance is an ionic solid. Ionic solid. Okay. Now, first of all, oh sorry. Okay, it's fine. First of all, ionic solid. Okay, ionic solid simply states or simply means, okay, let's search this, and I can give you a proper definition. So ionic, what was it, sorry, this is ionic solid. Yeah, ionic solid. Hopefully you guys can see this. Let's just move it right there. So ionic solids simply are made up of positive ions and are held by electrostatic attractions. They have very high melting points and they're poor conductors in the solid state. Okay, so poor conductors in solid states, that's what we're looking at, poor conductors in the solid state. Okay, so as you guys can see in this sort of example right here, okay, the answer could be B. Okay, the answer could be B because first of all it says that in solids they're not good at conducting, right? And because of that, you can see it does not conduct in this. But at the same time, it was saying that they have very high melting points. 777, very good melting points. So the answer is B. Which substance is a liquid at room temperature? Okay, so this is quite straightforward. You can say that because, you know, melting point 190, 190, negative 94 and 63, this one could be the best. Okay, because if you've seen the other ones, they all have very high melting points and very high boiling points. They're just out of the range. So the answer for this one would be D. Which substance has a giant covalent structure similar to that of a diamond? Okay, and let's remind to ourselves what is a giant ionic, sorry, was it um, giant covalent structure. Okay, so let's have a look at giant covalent structure. So there you go. If you guys can see that, a giant covalent structure is a three-dimensional structure of atoms that are joined by covalent bonds. Okay, so they're joined by covalent bonds, and allotropes are different forms of the element in the same state, like graphite, graphene, and diamond. Okay, so let's have a look at the characteristics of this. Okay, because that's what we are interested in, characteristics. Okay, they are solids in room temperature and high melting points and boiling points. Okay, that's going to give it to us. Okay, solids at room temperature. Okay, so let's see which one is solids at room temperature. So they all are solids at room temperature. That doesn't give us, but they have high melting points. That can give it to us. High melting points and boiling points. So this one has the highest melting point, so it should be E. Because it says similar to diamond. Diamond has a very high melting point, so it should be the same. Which two substances could exist as a simple covalent molecule? Okay, simple covalent molecule. Uh, Basically, this should have, both of them should not conduct electricity in any form. So that should be A and D. So the answer is A and D. Okay. So you know, that was just a few questions that are related to this. So hopefully you understood, you know, a bit of it. So let's do like a rate of a reaction question. Okay. and hopefully we can do something from here. But before that, let's see if we have finished the rate of a reaction. I think we should have finished rate of a reaction, and pretty much that must be it with rate of a reaction. Let's just bring that back to the center. And let me just look at the topic outline. Okay, yeah, after this we have simply reversible reactions. So now I think we have the ability to finish all of these reactions, because next up is reversible reactions. Okay, so let's have a look at some questions on rate of a reaction. Okay, so rate of a reaction. So it says, okay, when an aqueous sodium thiosulfate. Okay, let's see if we have any multiple choice. Okay, yeah, we do. We do have some multiple choice. So why don't we do some multiple choice first? Okay, that's a good sort of way to sort of answer this stuff and to understand better. Okay, so we start. A liquid X reacts with solid Y to form a gas, which the diagram shows a suitable method for investigating the rate of a reaction. Okay, so this one I believe we have done it. Believe we can answer it. Okay, so basically in this question we're looking at a way we can maybe collect a gas. Okay, we can collect a gas. So when we are collecting gas, because it's saying this is the keyword, to form a gas, and to form a gas we need a gas syringe. It's logical to have a gas syringe. Okay, and therefore the answer is one. Sorry, it can't be one. You know why it can't be one? Okay, it can't be one because of this cotton wool. We can't be one. Okay, but we need a gas syringe, so we know we need a gas syringe, so it's either this, so we need number 4. Okay, and number 3, we do not sorry, let me try and rephrase what I just said. Now the difference between 1 and 2, okay, we need a balance first of all. Okay, and the difference in these two is that this one's cotton wool and this one is a gas syringe. Now why number 2 will be correct is because all this gas will be collected in this cotton wool, will increase the weight. Okay, and this can show that there's a change in the rate of reaction. So therefore 2 and 4 will be the correct answer, because we need a gas syringe. Okay, the next one says an experiment S is carried out to measure the volume of hydrogen produced when excess dilute sulfuric acid is added to zinc. Okay, and then we have the results of the 2 experiments are shown. So which changes in the conditions between experiments S and T give curve T? Okay, now I'll just do a few questions because it's a very, very long sort of question, but you need to just get the idea of this in such types of questions. So first of all, in this type of question, it's saying that is carried out using the same mass of zinc, okay, but in different conditions, which will basically give, which experiments between S and T will give curve T. Curve T, remember we decided this has a lower gradient. When this has a lower gradient, if the zinc, for example, is very big, okay, that will lead to less surface area. Okay, so the answer in this one should be, I believe, you don't need an additional catalyst, okay, but the answer should be C. Okay, so that's just do about 2 questions, and that will be good enough. Now, in the next live stream, we'll have a look at reversible reactions. That was a quick live stream, and I hope you sort of enjoyed this short live stream dealing with the rates of a reaction. Comment down below if you want me to do some more rates of a reaction questions, and I'll be, sure to do more of these types of questions. So, thank you for watching this live stream. Hopefully you guys enjoyed it, and I will see you in my next live stream. So, thank you for watching, and goodbye.